Now, the remaining terms have been given the name twisting, and that leaves us then with bending and twisting effects. And you can show by integration of parts that the total contribution to the energy of the plate is zero for the twisting terms if the plate has zero deflection all around the boundary. And it's a nice way of dividing the energy content in the plate into bending and twisting, and it also simplifies this calculation for many practical problems. So we have an expression now for the strain energy in a plate. I've seen many textbooks that use the moment curvature approach to calculate that energy, and in fact we're also going to use the moment curvature approach in development of the Marash-Zienkiewicz-Chung rectangle in the following lecture. Therefore, it's probably good to see the alternate way to find strain energy. Here's the expression, and this time you're integrating strain energy in the form of a moment times a curvature integrated over the plan area of the plate. When we put in our moment and curvature formulas that we had found from equilibrium arguments, we find that we'll get the same expression as before. So you'll get the same U as before. We'll be using the final expression for strain energy in some Rayleigh-Ritz problems in the homework. Now let's look at in-plane stretching of flat plates. We've already defined what the in-plane resultants are. These are integrated values of stress over the cut edges of the plate. We'll look at an infinitesimal element and get a force balance. Here you see, for instance, on the cut face perpendicular to the x-axis that we define the dominant force Nx, but it has a small increment showing the change from the reference side on the back. Likewise, the tension in the y direction, and then the shear. Now we use a moment equilibrium within the plane to equate the two shear forces, and then we use equilibrium in the x and y directions to get the equations of equilibrium for that infinitesimal element. And here are those equilibrium equations. The one for the x direction and the one for the y direction. And these are very similar in form to the plane stress problem. In fact, you might even call this an average plane stress problem. The boundary conditions involve both the in-plane displacements and then the in-plane force resultants at the boundaries. Generally speaking, this membrane problem that we're speaking of here is underestimated in the university teaching of theory, because we often deal a lot with the bending problem and not so much with the stretching problem. And yet there's a lot of design done out in the field, for instance in the aircraft industries, where membrane theories are used to represent the thin-walled monocoque structures. So membranes in 3 dimensions really are important, where this in-plane force balance is really the dominant effect. Now, you know that there can be a coupling between the in-plane forces and the out-of-plane deflections. That's considered a mild nonlinearity, and we don't discuss that here. So in the context of this particular set of lectures, we assume that the in-plane and the out-of-plane problems are completely uncoupled. I'd like to call that a linear infinitesimal theory, as distinct from the coupling effects that start coming in, and sometimes people call that small deflection theory. Terminology can be a problem, but be sure you understand from the context of the situation whether or not you're accounting for that mild nonlinear effect of the in-plane forces affecting the out-of-plane displacements. Many times in practical problems, an engineer will pose a force field as if it's a concentrated lateral force. And this puts pressure on the mathematical methods to handle that singular loading relation. One way to do the problem is to convert your loading into a force times a Dirac delta function, where the Dirac delta function is a mathematical trick for handling such singular loads. The Dirac delta function is given the symbol delta and has an argument of a variable x minus some reference point. The function is really defined in the limit as a series of such spikes where the amplitude of the spike grows and the width of the spike diminishes, meanwhile keeping constant area under the curve. And so in the limit then you have just a very, very tall, thin spike at this point right at x0. It's often used then to express, say, a lateral load as a constant, say 50 times a Dirac delta function in the x and then a Dirac delta function in the y directions. Now, two important integrals that you should understand thoroughly are that the definition of the Dirac delta involves the integral of the function itself on the line here, and it gives a unit value, and that's the area under the curve shown cross-hatched in blue above. But secondly, in the application you find then, often in calculating external work, you'll have the product of a Dirac delta function times some general function here, which might involve force-like and displacement-like quantities. And the Dirac delta function is very selective. It will choose then, by acting on this function, to emphasize only the functional value at the reference point x0, and it selectively picks out the function at x0. You can show that by taking a limiting process where you integrate from, rather than 0 to L, you can start closing down where you integrate from x0 minus some very small epsilon quantity to x0 plus epsilon, and then you can expand your function, if sufficiently smooth, in a Taylor series, and then show that this literally is true. This is the dominant term here. Problems 1 and 2 in our problem session comprise a study of a square plate under lateral loading, but the loading is taken in two different forms. In the first problem, I use a lateral concentrated load of 50 newtons placed at the center of the plate. Then in the second problem, I distribute that load over a wheel print, a footprint, such that it represents what a tire might press on the plate. The idea is to see the difference in severity of the loading between such a concentrated idealization and then a more rational distributed load. In problem 1, I'm going to take the 50 Newton load and apply it at the center of this plate. The plate is 1 meter in both plan dimensions. It's simply supported all around, and the plate is 5 millimeters thick. It's steel with given Young's modulus and Poisson's ratio, and we're given the flexural rigidity. The goal is to find the bending stresses at the center of the plate, and we are interested in an approximate answer. If we bake the same modeling assumptions into both of our solutions, then that should help us look at this in the sense of a parameter study, such that both answers have errors probably in the same direction. Because we're interested in an approximate answer, I'm going to use the Rayleigh-Ritz method, which is the direct variational method using potential energy. I'll only carry one assumed term for the deflection field. So here's the assumed deflection, a constant, times two sine functions with half wavelengths across the plate's dimensions. We can see that z is positive upward, and therefore this deflection will probably yield a negative number here for the coefficient capital C. A major ingredient, of course, is the strain energy calculation, and here it's given in general. It turns out for this simply supported plate all around that the twisting terms will vanish, so we're left, fortunately, with only the bending energy to calculate. That's shown down below here in an expanded form, and then we put in the specific assumed functions here. In energy methods, one often gets integrals of squares of sine and cosine functions, and these have particularly simple evaluations. Here we end up with the sine squared integrated over the width and length of the plate. That happens to be a half wavelength in each case. Now, you can show that the sine function, when integrated over a portion of space in which it is occupying a quarter or half or full wavelength, will cover exactly half of the area enclosed within the rectangle. And so we make use of that and realize that our integrals are just a over 2 here. So the integral is quickly evaluated for strain energy. Now the work potential is the negative of the force times the displacement on which the force acts. So remember, it's the magnitude of the force times the distance through which the body moves. Now we can evaluate that directly here by looking at our sine functions right under the load, and we get this contribution. We then can add the work potential and the strain energy to get the total potential energy, and that's shown here. It's indeed a quadratic function, quadratic in the displacement capital C, and now we need to take a derivative here to make a stationary value of potential energy. To find the equilibrium of a structure using potential energy, you take the first variation of potential energy and set it to be 0. Now we only have one coordinate in this problem, that capital C, and so basically we'll be setting the first derivative of potential energy with respect to C equal to 0. That's done here. When you do that and carry it out, we have a quadratic term here and a linear term here, and they both are knocked down 1 degree, so you get a linear equation. You solve for C. Then when you put in these values for the physical constants and then take into account the fact that the load is in the negative direction, then you get this expression finally yielding 0.216 millimeters downward. Now that is really the multiplying coefficient on the assumed displacement field, and of course has the extreme value at the center of the plate where it is exactly 0.216 millimeters. So in this case, the constant carries the length scale, if you think in terms of dimensions, and then you have to evaluate it at the relevant point in which you're interested. We'd like to find the stress under the load, so we'll use the stress curvature relation that we developed earlier. Here's stress as a function of the curvature of the neutral surface, and we have a solution for that now, so we can substitute values. This is general for any point in the cross-section of the plate. Let's look at the top surface where we take z equal to plus h over 2, and that's going to lead, it will turn, to a negative stress because for this load there's going to be compression on the top fiber. We put in our recently found deflection values, take the proper derivatives, evaluate the physical constants, and then arrive at this 1.58 megapascals in compression at the top fiber. Of course, there'd be tension of an equal amount on the bottom fiber. Now we want to remember this number and carry it forward into our second problem to see how the number changes when we use a distributed load. Problem 2 considers a square plate with a distributed load over its center. And the load pattern is meant to represent the tire footprint of a vehicle on the plate. The footprint will be 200 millimeters wide by 400 millimeters long and centered on the plate. The total load will be 50 newtons spread over that area. The plate is the same one as in plate number 1. It's a meter in plan dimension, square, and then 5 millimeters thick. So the question is, what is the maximum deflection in this case and the stress under this footprint? It's not quite so clear that the maximum stress would be at the center now, especially if you did a more exact solution. It could well be that the maximum stress would be around the periphery. But because of the simple one-term solution that we're going to use, I suspect we'll get the maximum stress at the center of the load, where the maximum curvature of the assumed deflection is. We'll again use a one-term potential energy solution as we did in the concentrated load case. Here's the same deflection function. And we don't need to calculate the strain energy again, because in terms of the unknown coefficient C, the expression is the same. Now, we will get a different solution for C, but the general formula is identical. This time, our work potential is more complicated because we have to integrate the lateral load against the deflection. Again, we put the assumed deflection into the formula with its unknown generalized coordinate. Put in the surface pressure this time, which would be that 50 newtons divided by the area. And we may as well integrate only over the load pattern, you see. Otherwise, it will extend this pressure field more broadly. So rather than deal with a discontinuous function here over the whole plate, sort of in the Dirac delta spirit, we will do the opposite and bring the limits of the integral in tight to the load pattern. In evaluating the work potential, this time we don't end up with nice integrals over, say, a half wave or a quarter wave. This time we have to actually work at it and analytically integrate. We find that we get sines converted into cosines upon integration and have to do the differencing between the limits. And then finally we end up with this expression for the work potential. It has a constant C, which is a generalized coordinate. We form the potential energy again by the sum of the strain energy and the work potential. And we have a quadratic form here, a quadratic term and a linear term. We take the first variation, which implies that the first derivative should be 0 at equilibrium. We evaluate those coefficients, and we find that our deflection is minus 46 a squared pi to the fourth d. And we find that that is 0.198 millimeters, which is some 8% lower than the case that we had previously for the concentrated load. Now, it turns out that because the single displacement field has this coefficient times the predetermined sine function, that the maximum stress in this problem with this solution approach is still under the center of the load pattern, and it also will be 8% lower. Problem 3 considers a rectangular plate with a concentrated load that's not at its center. The plate is simply supported all around. Here's the concentrated load, which lies at the midpoint in the y direction, but at the 3/4 point in the x direction. The plate has an aspect ratio of 2 to 1. And we're going to propose a somewhat more intricate solution this time than the previous problems, in that we'll have a two-term solution and we will use Galerkin's method. Now, Galerkin's method requires that these assumed modes independently satisfy all the boundary conditions, and they do. You can check and see that the sine functions have both zero deflection and moment at the boundaries. The goal is to find which of these modes contributes most to the deflection under the load. The first mode, for instance, has a half wavelength in the x direction and a half wavelength in the y direction, whereas the second mode here has a full wavelength in the x direction and a half wavelength in the y direction, which makes it negative here on the right side. And so the question as to which of these terms contributes more to the deflection will involve the balance in work done by the external force and then the strain energy required to move the body in each of those two modes. The load is actually a little more appropriately placed to do work on the second mode, but the second mode takes more strain energy. Galerkin's method uses the differential equation directly with a weighting function, and the weighting function is taken to be the same as the assumed deflection modes. Here's our differential equation, and this time I'm going to illustrate the Dirac delta function to show that the magnitude of the force can be multiplied by the Dirac delta in the two directions to concentrate that force at a point. Also, I'll use the series form for the assumed solution. The coefficients c sub I here are the unknowns and become generalized coordinates. Then we'll use weights that are also the same as the assumed modes, that is the Galerkin idea. And we will use the J index here both as 1 and 2 to get the half and full wavelengths in the x direction. This allows us now to use a summation form, shown below here, for the equilibrium of the plate. There actually are two such equations, and the original Galerkin's method that we're using then brings a balance about where the two weights here will allow us to have two equations, and thereby letting us get enough information to find the two generalized coordinates. The integral calculations are a little bit tedious, and I'll move quickly through those. The first term in the equilibrium law involved the del fourth term. This actually can be shown to be related to strain energy, although it's not posed that way initially in the Galerkin's method. And those derivatives then act upon the x and y coordinates internally, but they replicate the sine functions again, such that the integral now becomes a form where you have the series of coefficients out front and then these integrals which are separated out. On the right side, you have to do the integration of the Dirac delta function, which selectively picks out the sine values at the loaded point, and that's done both in the x and the y direction. The y integral with the Dirac delta is particularly easy because you have a load that's centered on the y coordinate at the maximum deflection point where it gives a unit value. But the expression for the work being done here by the force integrated over the x dimension requires that you evaluate at points that are not just unity. We need to evaluate those integrals on the left side of that expression, and they involve products of sine functions in both the x and the y directions, and both with the same wavelength and different wavelengths. We can use some of our rules of thumb that we'd talked about earlier about how you get half of the enclosed area under a rectangle when you're integrating sine squared terms, and that shows up here where we use the Kronecker delta, which has a unit value when I equals j and a zero value when I is not equal to j. So this helps on the integration in the x direction. Then in the y direction, we have the same wavelength. We're then able to write out our resulting algebraic equations that Galerkin's method has provided. There are two equations. In general, you would expect them to be coupled, but through quite a fortuitous event here, you find that the off-diagonal coefficient terms are 0, and the two equations uncouple such that the first equation can be used to find C1 and the second equation can be used to find C2. On the right, we see what you might call generalized forces, and we see that the generalized force in the first equation is a little smaller than that in the second. Also, the first one's negative because the force is in the opposite direction as the assumed mode shape, the first assumed mode shape. I'll rewrite those equations here in simplified form. And we have the two equations, and you have something like a generalized stiffness and a generalized force involved. When you solve for the coefficients in terms of these symbols, you'll get these two results. Now, at this point you might say, well, it's pretty clear that the first mode participates more. Yes, there's a higher coefficient in the first mode than the second, but now we're supposed to look at the contribution to the deflection under the load. That was our goal. So let's look at that. To calculate the deflection under the load, we have to look at both the shape of the assumed modes and their coefficients. Here I sketch the shapes in blue and then show the coefficients out front, which we now know. If you account for the shape, then that evaluates the sine functions under the load and gives these numbers here of 0.707 and -1. If we then put in the known values for C1 and C2, we can evaluate the deflection in total. The components are that you have this contribution from the first mode and this contribution from the second. They do both contribute a downward deflection, but notice that the coefficient is a little larger in the first mode than the second, and then you have common dimension quantities following. So we can conclude that the first mode contributes 28% more deflection than the second mode. And I show the combined picture below with the combined deflection under the load. So that ends our problem session. Plate